Welcome back. One of the most important topics in geometric measure theory are projection theorems. Take the example of a subset of R2, this E, the dust of points that I have drawn here. Fix a angle and a line through the origin making that angle. This line is a copy of one-dimensional Euclidean space, and we orthogonally project every point of E onto this line. For example, this point has projected down to this red point. So the projections are here denoted by, are drawn in red, of course living in the blue line. The question is, the overarching question is, what can be said about dimension of the projection of the set, here projection onto this theta, in terms of course, dimension of E itself. And here, dimension of E can be anything beginning from 0 up to 2. We know that it cannot be bigger than 2 because the whole space R2 has dimension 2. And the phenomenon that occur is actually quite different when dimension is equal to 1 and less than 1 and bigger than 1, as we will see. In each category, different things happen. But before we present the very main theorem, let's look at the basic things we can say. Number one, in general, you cannot guarantee anything for all angles. So suppose you have the best possible scenario, you have a straight line. Okay, so if this is your set E, it's one-dimensional and everything nice happens for the set. But then if you take as for the line something like this, and then when you project it, it just becomes 1 point. So for some angle, even if your set is really nice, for some angles the projection could kill all of your set. But in this case, we see that it's only for one line that this failed, but you get the idea. So the results we will have will always be about almost every angle, almost every direction. And to make precise the meaning of what do we mean by almost every angle, notice that every line through the origin is uniquely identified by the point on the circle, almost uniquely because there is also this other pair back there. Either we identify them, we can say projective space, or why make things complicated, you can agree that the angle will be between 0 and pi excluded because pi now agrees with 0. So every line, every blue line through the origin is identified uniquely by the point in this range of 0 pi that it crosses through. So when we say almost every theta, we identify this, of course, this arc with the line segment, say, from 0 to pi. And then you can even identify it with 0 to 1, and then you just talk about Lebesgue measures. So it all makes sense to talk about almost every angle. In the previous example of the line segment that I drew, in one very specific direction, the projection is 1 point, but in almost every direction, for example, if you take this very blue line that I have drawn, the projection is not degenerate, and it is also one-dimensional and has positive measure as well. So many of these phenomena we will see and explain why this happens for this line segment. Okay, so one basic lemma, I have covered this in the study of Hausdorff measures. If you have any Lipschitz map, this is very general, between two metric spaces, is Lipschitz, L Lipschitz to be specific, and S is any number, and E is any subset of X, then the Hausdorff S measure of image of E is no bigger than Lipschitz constant to power S, the same Hausdorff measure of what you started with. And this is just an easy exercise by definition of Lipschitz and Hausdorff measures. Probably I also have covered it in one of those videos. So why is this relevant here? Because in our case, the projection onto this, this is from R2 into R1, basically the blue R1 copy of that, is 1 Lipschitz. It never increases the length. This is just Euclidean geometry. So HS measure of the projection onto theta of E is less than HS measure of the E itself, with no restriction on theta. It's not almost every or anything. Every projection is 1 Lipschitz. For all theta, all subsets of R2, no regularity, no dimension assumption, and all S, integer, non-integer, whatever. So a corollary of the corollary then is that the Hausdorff dimension of the projection of set is never bigger than the dimension of the set you started with. Because if this is T, then HT plus any epsilon of this projection by definition of Hausdorff dimension would be infinity, but then this is less than or equal to HT plus epsilon of E itself, which means that this is also, so this gives the lower bound of T plus epsilon on dimension, but epsilon is arbitrary, so you get that Hausdorff dimension of E is at least T. But as we saw with this example of line segment projecting to a point, that this can be strict. So sometimes, so proof here. So we see that sometimes actually you get a much smaller dimension for the projection than for the set E. The best way to really understand the next theorem is for you to maybe pause and think a little bit about different phenomena that can happen, and try to come up with examples of sets with weird behavior under projections. So I'm going to code, I will be actually more often coding Falconer than Mattila, because he presents things in R2 first, and then dimension S between 0 and 2. And then he comments on higher dimensional analogs. Sometimes the higher dimensionals follow from similar argument. Sometimes they need much deeper and more difficult proofs and machinery. Again, he makes very beautiful commentary paragraphs about that. So Falconer's book is a bit easier, as it does not cover all general cases. But then the benefit is that it's easier to read, and it's also a much shorter book. So what is this theorem? If E, a subset of R2, is a Suslin set, okay, if you don't want to think about it, this collection of sets definitely includes all Borel sets. So I've never defined Suslin set, and I won't get into that right now. So if it is, say, just Borel set with dimension of E equal to S, so definitely S is between 0 and 2, then there are two parts. If in the case in the regimen S less than or equal to 1, that means we are smaller. Think about the line segment or a smaller set. Then for almost every angle, what is your guess? Try to guess. What is the claim about the projection onto theta of E? Okay, maybe this a little bit of picture will help. So suppose we have a set that is less than one dimension. It has some fractional dimension like a counter set. And then you project it onto some line. Can the dimension go straight? So we saw that dimension is at most S. Can it go strictly down? Definitely. Again, you can think of a few lines. I mean, well, not dimension 0. You can think about a dimension, say, 1/2 set, which is contained in a vertical, in a line segment like this. Then the projection will be 0. So it can definitely drop, but then for almost every theta, this does not happen. So the claim is that for this set, the projection actually does not drop the dimension. The set is S-dimensional, and its projection is also S-dimensional. Maybe not for all theta, but for Lebesgue, almost every theta, this is the case. Not trivial at all. Now, what happens in the case S is strictly bigger than 1, which, to be more precise, let's say, I mean, not let's say, S is definitely less than 2, but what happens in this one? Now you're talking about sets that are larger than line segments. So maybe kind of a counter set style thing. Of course, this is dimension 2, but imagine this is a step in the construction, and then you remove more points from the middles and stuff like that. Then for almost every theta, dimension. Okay, so here's the claim is actually more. So if you project a set here, the claim is that it has dimension 1. But having dimension 1 doesn't mean its measure is positive. But in fact, for this theorem, the claim is that indeed, not only you have dimension 1, you have positive measure there. So L1, which is just H1. So L1 of the projection, actually I prefer H1 because this line theta is not exactly R1, it's a copy of it. Well, they are the same anyway. So, but let's put Hausdorff measure. So projection onto theta of E. So for almost every theta, when you project E onto that line, not only will have dimension 1, its measure will be also positive. Notice that HS of E itself could be 0. S could be S-dimensional, but with 0 measure. The projections do have positive measure. Here, of course, the key is that it's strictly bigger than 1 and not equal. Okay, so two very, very important parts. For small sets, projection does not drop the dimension. For large sets, the projection is significant. And both claims are for almost every theta. The proofs of these original proofs are due to Marstrand, circa 1954. Then proof using potential theory, and this we mentioned before also, that this notion that okay, these both of these statements concern the dimension of some set. Then we saw that for Borel sets, say that the Hausdorff dimension and the capacitor dimension, which was defined through some crazy stuff from potential theory. So S energy of a set was this, of not set of a measure was given by integrating d mu of such thing, and then you looked at their inverses, and then you take supremum over the set of all measures that are supported inside E and whatnot. But anyway, that is the link. And when potential theory comes in, you can talk about Fourier transform and things like that. And this gave a more elegant, say, proof of this result. And that was discovered by Kaufman. So in Falconer, for dimension other than s equal 1 non-integer case, so when s is strictly less than 1 or bigger than 1, they follow this Kaufman argument. For the integer case, they say they follow the original proof by Marstrand, which is more geometric. Okay. Of course, this leaves many interesting cases, especially when s is equal to 1. So in s equal to 1, we know that the dimension of the projection is 1, but is the measure of the projection positive? There are many there are cases of sets where on some projections you get positive measure, on some projections you get 0 measure, and this is actually quite interesting and research level question of identifying conditions under which you get a one and not the other. Okay, I think this is enough for a start on projection theorems. In next one, I can talk about the higher dimension and analogs. The statement will be very similar, but we have to make sense of what do we mean by almost every subspace, and that's an interesting construction on its own that everyone should learn about at some point. Hopefully some of you have already seen what a Grassmannian is. But until that, I leave you with this beautiful theorem, and I recommend you play around with some counter sets and other examples we had on the channel and apply to see if this provides any non-trivial facts about those sets. Until then, thank you, and by the way, thank you a lot for everyone. We are getting very close to 400. Maybe by the time you watch this, we are 400. That is amazing. When I started this channel, I wasn't saying that there would be 400 people who would care about Hausdorff dimension of projections onto almost every line in R2, but definitely it's beautiful stuff. Thank you. Have a great one. Please consider subscribing if you haven't already. Bye-bye.